So welcome everyone, and welcome to this presentation. And as Joao said, today we will be talking a little bit about aerial simultaneous mailing and mapping. And I'm going to frame this a little bit into the development of an autonomous aerial smelling robot. So let's get to it. So the first question that we have to answer is why, right? Why is this useful and why is it needed? Well, aerial smelling robots are mainly used for air quality monitoring, and air quality monitoring is an essential tool for controlling either anthropogenic and natural emissions for the atmosphere. Now, these polluting emissions not only have a harmful effect on human health and climate change, but they also affect production of agricultural yields, and they can reduce visibility, snow and rainfall at sunlight at ground levels, which is sadly enough a sight that we have grown accustomed to. So, can UAVs be a solution? Well, certainly not as a solution to the actual problem, but they can be a way to monitor and control these emissions. UAVs, aerial and unmanned aerial vehicles, are quickly becoming one of the main sources of air quality monitoring in aerial imaging surveys. And this is basically because of their small size, their flexibility, and ease of deployment. And you can see some examples in the pictures that you can see in the presentation, where you can use a UAV to get water samples from a hard to reach body of water for inspection of gas installations or volcanic emissions near volcanoes. Now, regarding these smelling drones, this has been possible thanks to the miniaturization and development of this gas sensing technology, right? And it has led to gas sensors of a very reduced size and weight, which makes mounting these gas sensors as payloads in the drones very easily. In the end, what we have is drones that are cost and time efficient, and they're a good way to increase the amount of gathered data. This, as I said before, these gas sensing robots have multiple applications, and I'm going to bring it home a little bit with some applications that we have developed in here in Wageningen University. And some examples of these applications are its use in agricultural fields, right? To do gas surveys over agricultural fields, which can help you monitor and detect crops' health. And also, they can be used by fire departments in firefighting efforts. And here's an example of a drone that is currently being used by the fire department of Twente with very successful results. And before we continue, we have to address the elephant in the room, right? So, what about the rotors? I have a gas sensor and I have a drone that is obviously moving a huge mass of air around it. So, what do we know about this? There are examples of these gas sensing drones in the literature, apart from our works, and most importantly, the effects of the rotors on this underlying gas distribution has been studied extensively. And this is obviously important as the rotors do disrupt the wanted readings, right? So as it is, these results from the literature state that although readings from the airborne gas sensors are usually lower, sometimes 2 to 3 times when the gas plume is small, in the end, the underlying gas plume structure and the peak concentration readings can still be obtained using them. This is also alleviated in the case of huge gas plumes, or in cases where the actual concentration is not necessary. For example, let's say that you just need to meet a threshold concentration, and you know that all of the readings above that are what you're looking for. And in that case, this high precision is not really needed. Yeah, so let's continue. And now that we know that we have a way to get these gas readings, we need a way to model it, right? So let's get back on track with the title of the presentation and think about how we're going to map this gas in a way that is useful to us. Now, regarding gas distribution modeling, there are usually two main approaches. We have model-based approaches that are such as fluid dynamic simulations, but in this case, these approaches really do not scale well in size and are very, very computationally expensive, which means that in a live setting, they are not really usable. And on the other hand, we also have model-free approaches. These model-free approaches, what they do is that they treat the gas readings as random variables, and what you end up with is a probabilistic model of your gas concentration in a given space. Regarding these model-free approaches, there are two mainly used two mainly used two mainly used approaches. The first one is the simple Gaussian process mixtures, and the second one is the kernel DMV. And now between these two, the one that we are going to use in this case is the kernel DMV, because it provides a similar performance, but its complexity scales much slower than its counterpart. And for this live setting that we want, we will have a much better performance. So let's have a quick talk about the kernel DMV. It was developed by Lilienthal and Duckett in 2004. Apart from the 2D version, it has further extensions that allow you to map 3D spaces, time varying concentrations, and also include wind information. And what it basically does is that it gives you a probabilistic predictive model of reading R at given location X based on all of the previous readings that you had. And since this is a little bit vague, I'm going to show you what you end up getting when you use the kernel DMV. So in this slide, what we have is a ground truth, which is just a gas concentration. And what the kernel DMV gives you is these three maps. It will give you a mean map, a mean concentration map. And I don't know if you can see it, but all of these small pink dots are locations where we have taken a reading. So what you end up is these three maps with a mean concentration map, a variance map, which gives you the expected variance of the reading at that location, and the confidence map, as you would expect, it just gives you how confident you are on the readings at that area or location. All right. So what do we actually do in the end with these maps? So we know that we have seen a way to smell this gas cloud using our UAVs, and now we have this way to map this gas cloud into a 2D or 3D space. But we still need to do both at the same time and know where to take these gas measurements. And for this, what we're going to do is we're going to try to describe locations where we want to take these measurements, right? We want to know if measuring in an X location, so if measuring here or measuring here, is going to be useful or not. And first, we need to describe utility. We need to describe what is useful. So to do this, there are various approaches. There are some information theory-based approaches, such as Shannon's entropy or mutual information. But its implementation is complex, and in this case, it doesn't suit well the probabilistic model that the kernel DMV gives us. So what we end up with is having a heuristic approach. Now, this little equation is actually a very simple equation. And what we see is that we can obtain a utility map that I've called U, just as the sum of the weighted maps that the kernel DMV gives us. Right, so this utility map is just the sum of the confidence map weighted by a beta weight, the mean map weighted, and the variance map weighted. And as you can see, the utility map that you end up with, where the pink line is just the path that the drone has covered, you can see how areas where we haven't been have high utility, and you would expect a high amount of information to be gathered there. Areas where I have been have a low amount of information, and areas where I have been, but as you can see, I know that there's a small gas plume, have a medium level of information. So you can leverage these varying amounts of utility, and you can use them to plan to plan on this utility map. Obviously, this utility map, every time we take a measurement, and this is where the life part comes in, this utility map can be updated, since every time you take a new measurement, you can input that into your kernel DMV, and it will give you an updated representation or hypothesis of your gas concentration. So, as I said before, we end up with this utility map, but now we need to move through it. And to do that, we're going to use informative path planning. Now, contrary to traditional path planning approaches such as A star, where you just have a starting point and an end point, and what you want to do is find an obstacle-free trajectory to get to the end, what informative path planning seeks to do is to maximize the amount of information gathered along its trajectory. So here you can see a small video of ACLOP, which is an informative path planning algorithm that we have developed. And you can see how, as the drone moves and the planned path is updated every time we take a new measurement, because our hypothesis and our map of the gas concentration is new, the utility of that location gets lowered. So every time we take a reading, we expect that the information at that position would be lower, and thus what we will want to do is to move to a location that has more information. And well, that actually covers the starting theoretical part of this presentation. So now we can get our hands a little bit dirty with the integration of the system. As I said at the beginning, at the start of the presentation, I was going to frame this into the development of an autonomous gas sensing drone. And with this drone, what we're going to do is we're going to deploy this simultaneous smelling mapping system that we have just described. And this is where we will be able to see how ROS can help us build this type of solutions very, very easily. So let's get a little bit familiar with the system and the tools that we have available. This drone that you can see here is our autonomous gas sensing drone. It's DJI M100. And as you can see, we have mounted a suite of gas sensors that allow us to read more than 12 different gases. And it can transmit these live readings directly to a ground station. And also, apart from DJI's own computing and autopilot, we have an onboard computer here on the form of a Raspberry Pi 3. And this will provide support as the link between our ground station and the drone's autopilot. So regarding the system setup, what we end up having is our ground station, which is just a laptop. And we have two wireless interfaces. One that is just a Wi-Fi connection that will allow us to link with the onboard computer, and another one that fits the sensor data. And obviously, the onboard computer will be connected through the through a CAN and UART connection to the DJI's autopilot. And well, on the other hand, we also have our typical RC controller with our video downlink, which in this case, it will just act as a fallback in case of an emergency. All right, so with this big picture, let's try to wrap our heads around what we're going to need to run to complete this system and success on our mission. So this is our system architecture. We have an airborne site where we have our DJI onboard SDK. I will talk a little bit about it in a little bit. That is going to run on our Raspberry Pi, and it will connect to DJI's autopilot. And also in the airborne site, we have our sensor array that has this wireless link that will feed us this sensor data. So what we're going to do with this sensor data is take it, process it into something that the kernel DMV can understand. Then we are going to calculate our utility map, run it through our path planning algorithm that needs this utility map that we have calculated, along with the telemetry, as the path planning algorithm needs to know where it is in order to plan for the next coordinates. And with this, we can obtain these next cell coordinates that need to be processed into something that the DJI onboard SDK can understand, right? And that would complete the loop. All right. Um, so as you can see, I have color coded these arrows, and what you can see here is that the blue arrows is what I expect ROS to take care of. So I don't really want to deal with this communication and have to build a complex communication system between all of these small modules. So how do we do this with ROS? And let's first have a very quick recap, as to not repeat myself with what we have seen this morning. So ROS, the robotic operating system, allows us to build a system of connected nodes and topics. We know that a process or an application runs in a node. So what you should think of a node as a single process or application that has some inputs and outputs. And this node can publish messages to a topic. This node can subscribe to a topic to read any messages sent to that topic by other nodes. So that's the way that we complete our communication system. And we know that the messages that are published to this topic can be of various types. So you can have single values, vectors, matrices, etc. Um, and here we have just a simple example. Just go through it very quickly, but in this case, what we have here is two nodes, a ground station node and an autopilot node. So as one would expect, the ground station will publish to a commanded position topic a simple message, which is just the x, y, z coordinates, and your autopilot would subscribe. So this is the way that you would convey this information from the ground station node to the autopilot node, which, remember, are just like a single application or a single process. And then, on the other hand, the autopilot does publish some position and velocity information, which is its actual position and velocity, and you would expect your ground station to be subscribed in order to either show it or do some processing on that data. Okay, so let's get back to our example. And here we have this same system architecture, right? But as you can see, I have done some boxes around some of these elements of the graph. So what I have done here is I have divided our system into single processes and small applications that I know that they perform a task and have these different inputs and outputs. And this is how the actual ROS application would work. So let's start on the left side first. And we know that our DJI onboard SDK that is going to run on our Raspberry Pi will conform a single application or a single node. We also know that our sensor data processing will also conform this other single application or single node. We can join all of this path planning and processing and gas modeling process into a single node, because we know that it's just going to take because we know that it's going to take these two inputs and this one output, and we really don't care about these internal communications between them because they are not useful to the outside system. And we finally have just a command, this DJI command processing node. So as you can see, the overall system architecture of the system is quite simple. And if you've noticed, I haven't made any particular mention to having this ROS network spanning across two separate systems, right? This is running on my computer, and this would be running on the Raspberry Pi, which is flying on the drone. And well, this is because once you have your ROS network set up, which in this case, if you remember, this connection is just a Wi-Fi connection, a simple Wi-Fi connection between these both computers. You can just have a seamless and effortless implementation, and you indeed do not require any complex custom communication system and any of that hassle. ROS will take care of that for you. And well, some exercise time. All right, let's have an example. So currently, due to the current restrictions caused by the COVID-19 pandemic, we have and should limit non-necessary interactions. However, we know that you can keep your research using a simulator. So how would you modify the current ROS graph that we have seen before, that I'm using for the real application, knowing that you have a UAV simulator that subscribes to a command topic and publishes to a telemetry topic, and a gas modeling simulator that publishes a gas reading given its position. I will give you a couple of seconds to think about it and think about what parts of the system should change, what parts of the system really do not need to change, and what type of connections you need to rethink. All right, so this would be the solution, and as you can see, it's a very similar graph. The first thing is that I'm going to run all of this on just on my computer, but this doesn't mean that you cannot move, as I said before, as the ROS network will allow you. You can always move all of these nodes to other computing units in case, for example, if you have a server at the university and you want to use that server for simulations. And as you can see, the only real changes, and I have highlighted them in red, are that instead of having our DJI SDK that will communicate to the real drone, we have substituted it with just the UAV simulator. And we know that this simulator is subscribed to a same commands topic. So this command processing would need some small tweaking, but you just need to transmit this information in a way that this topic and this node understands what you're trying to convey. So in this case, it could be just simple XYZ coordinates. And we also know that this simulator publishes its telemetry to a same telemetry topic. And what has changed in what was before just the ground control station is that instead of having our gas sensor readings, right now we have a gas model simulator. And we know that this model simulator does need some kind of input from the outside, which is the position. As if you have your simulator, you need to know where do you want the concentration from. So you would need some X, Y, Z coordinates, and you will obviously get them from this sim telemetry topic. And then this gas sensor model simulator just fits to this sensor reading topic with which can be the same as we had before, and that way we can close the loop and with these small modifications have this system architecture that we had for the real development into a simulation architecture. And I'm going to show you actually this live, and this is what I'm actually using right now, and it's running on this same architecture that we have seen on the last slide. I'm using RVs as my visualization tool, as my simulator. And what we can see here is the informative path planning algorithm running on ROS nodes, and all of the communication and the networking is dealt by ROS automatically. So here we have this mean concentration map that we are getting live. We have our confidence map to know on which areas we are most confident about the readings that we have, and here we have our utility map. Don't get distracted by the other two plots, as they are just the same plot but with different resolutions. And you can see how the drone traverses this utility map in order to obtain the most amount of information, as we have said before, from this utility matrix that we are updating every single time we get this new measurement. And well, that would be it for me today. So if you have any questions, I would be more than happy to answer them.